Mutual induction. In the figure, we saw that if two coils are close together, a standing current I in one coil will set up a magnetic flux phi through the other coil, linking the other coil. If we change I with time, an electric motive force epsilon given by Faraday's law appears in the second coil. We call this process induction. We would better have called it mutual induction to suggest the mutual interaction of the two coils and to distinguish it from self-induction, in which only one coil is involved. Self-induction here is defined as N phi over I. In mutual inductance, we have a similar definition. Mu 21 equal to N2 phi 21 over I1. Mu 21 is mutual inductance 2 because caused by 1. N2 is the turns of coil 2. Phi 21 is the flux through coil 2 associated with current in coil 1. And I1 is the current coil in 1. This is mutual. That's mutual. Okay. This is a definition. Okay. A definition. And we know that M21 multiplied I1 equal N2 phi. N21 is a constant, N1 is a constant. I1 can change, so phi 21 can change. We do the derivative with respect to time t on both sides. We have this kind of relationship. And we know that definition, the electromotive force induced in coil 2 by I1 is equal to minus N2 d phi 21 dt. And we look at this one equal to this one. So we get epsilon 2 equal to M21 minus di2 d1. This is electromotive induced by current change in coil 1. So this is di1 dt, and this is mutual inductance. This is similar to self-inductance, similar to inductance. Vice versa. So similar, if you change the current in coil 2, we can induce an electromotive force in coil 1. So we have epsilon 1 equal to minus M12 di2 dt. And M12 and M21 are same.
The high voltage for the spark plugs in a car is produced by a device called an induction coil. We'll use this induction coil to show the effect. Two coils are wrapped around a common iron core. The primary coil has a small number of turns made of relatively thick wire. The secondary coil has a much higher number of windings of thinner wire. This is a magnetic make and break switch. Current runs through the switch to the primary coil, and the magnetic field produced pulls the switch in towards the core, breaking the circuit. The magnetic field goes to 0, and the switch recloses, starting the cycle again. The pulsed current in the primary coil produces a high voltage pulse current in the secondary coil.
Sample. Figure shows two circular closed packed coils, 1 and 2. The smaller radius R2 with N2 turns being coaxial with the larger R1 with N1 turns and in the same plane. Question A. Derive an expression for the mutual inductance M for this arrangement of these two coils, assuming that R1 is much larger than R2. Okay, now we know the definition is N2 phi F2 over I. That's the definition. Okay, we find this one, then we can get it. Relate to I1. See the B1 inside. We learned this one. This is circle at the center, the B around this one. Okay, Z equal to 0. Because just on that surface. Then you get R1, 3, R1, 1, you get R1. Get mu Z, I1, N1 over C. You have N term, okay, N2. Okay. You got a B1, suppose it is uniform. So N2 phi x2 equal to N2 equal to, this is B1 multiply area, okay. It's very small, so we thought it's uniform, okay. This area is pi R2 squared. We get this, okay, and we use the B, put in the B. The B you have I1, cancel out this I1. Okay, we put the B inside. Okay, you get this one, put definition, okay, then we get mutual. Question B, what is the value of M for N1 equals M2 equals 1200 terms? R2 equals 1.1 centimeter and R1 equals 15 centimeter, which is much larger than R2. So we put the formula. By definition, M, mutual inductance, N2 phi 21 I1. Okay, and we have calculated that one before, right? Yeah, we put in the raised sign, we get the answer. Okay, it's about 2.3 million Henry.